Everything around us that we can see and touch, ordinary matter, is made of atoms. But one thing we know is, dark matter is not ordinary.
We know it's not ordinary matter because ordinary matter has this whole other variety of interactions. It has electric fields and magnetic fields, it emits light.
One idea is, since it's not made of ordinary atoms, dark matter might be made of some exotic particle. Right now, physicists around the world are racing to build a detector sensitive enough to capture one, so they can figure out exactly what it is.
It's working fine.
But how do you catch a particle that's so shy?
The fundamental problem is that this dark matter does not interact with matter very much. And so in order to detect it, we have to build these really specialized, very sensitive detectors.
At this underground lab, Tali Figueroa is monitoring one kind of dark matter detector, a superconducting crystal made from the element germanium. So one of your detectors, huh?
Yes, this is a prototype of one of the 30 detectors. And when you look at the surface of our detector, you'll see a metal grid.
The grid picks up tiny temperature changes produced when a particle hits the crystal and sets all its atoms vibrating. But to detect those vibrations, the atoms in the crystal have to start out as still as possible, something atoms don't normally like to do.
The problem is that naturally, at room temperature, the atoms are vibrating themselves.
So how does the team manage to slow down the detector's atoms? They put it in a freezer, a very powerful freezer. So the whole point of this is to simply keep the experiment cold.
Yes. We have to keep the experiment at about 50 millikelvin, which is 50 thousandths of a degree above absolute zero.
Just a fraction of a degree above absolute zero? Translated into Fahrenheit, that's like 460 degrees below zero. So in other words, it's cold enough so that the air we breathe freezes solid.
Absolutely.
And so there's frost everywhere. But now, there's another problem. The frozen detector is so hypersensitive, lots of things could set it off. Like cosmic rays, particles that shower Earth from space. So this is why the whole lab is deep underground. So the bedrock,
the half a mile of rock
above
is a shield.
Is a shield. So the cosmic rays, these are high energy particles from space.
From space.
Okay, so you're protecting yourself from space. And it's not just cosmic rays. Even underground, there are other tiny particles flitting around us, including photons and neutrons that can fly out of the surrounding rock. So the detectors are cloaked in layer upon layer of shielding, all in an effort to filter out everything but the dark matter. And how are things going so far? Okay, how many dark matter particles have you found so far?
None.
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 It's not too surprising. The quest for dark matter here on Earth has only just begun, and bigger and more sensitive detectors are already in the works. Still, you might wonder, could it be that dark matter is something that's just out there in space and not down here with us? Astrophysicist Richard Massey says, not likely. He's got the first ever 3D dark matter maps to back him up. But how do you map the unseeable?
So we can't see dark matter directly. It's completely invisible. But we can work out where it is by its effects on the ordinary matter that we can see.
In other words, you can see dark matter's gravity. That's because, according to Einstein and nearly a century of experiments, what gravity does in the universe is bend space. Massive objects like the sun actually bend and stretch the contours of space. That's what keeps smaller objects, like Earth, in orbit. And if space is bent, so is any light that passes through it.
So let's debunk the whole idea that light travels in straight lines. Light travels in what it thinks are straight lines. And because space is warped and bent, even the straight lines that light rays travel along are actually bent themselves.
The phenomenon is called gravitational lensing. Think of what a thick magnifying glass can do to the text of a book.
When we put a magnifying glass in front of it, we start seeing a distorted image. And gravitational lensing to find dark matter works in a very similar way.
A huge clump of dark matter and the enormous gravity it creates would bend areas of space so much it would act like a giant cosmic lens, distorting our view of distant galaxies. The more distortion, the more gravity, and, Massey assumes, the more dark matter lies between them and us.
So the final result is that we end up having this map of where the dark matter is in the universe.
Maps such as these are now revealing that galaxies like ours are completely enveloped by giant clouds of dark matter.
Wherever there's ordinary matter, so even here, there is some dark matter. It's everywhere. The two really have gone together hand in hand.
In fact, as the universe evolved after the Big Bang, dark matter may have served as a kind of cosmological glue that over time helped pull stars together to form galaxies.
We owe everything to dark matter in two ways. Firstly, it holds the whole universe together, but then it also, crucially inside that, it forms this scaffolding in which the ordinary matter can later grow.
We are so lucky to have dark matter because we wouldn't even be here otherwise. It was the gravitational attraction from dark matter that pulled together this diffuse gas that eventually formed our Milky Way galaxy that we live in. And if there were no dark matter, then our galaxy would in fact never have formed.
If that's true, then it's not just our Milky Way. Across the universe, none of the billions of galaxies out there would have formed without the gravity of this mysterious stuff. Now, we just need to find out what it is.
It's really astonishing that there's 5 times more stuff out there than we know of, and that we've been at this as a community for over 70 years, and yet it might be now in the next few years that we'll figure it all out. It's just incredible.